Well, welcome everyone to this new video where we discuss mathematics and physics on the board. In this video, we are going to continue our work on the Cauchy-Riemann criterion for analyticity in complex analysis. In a previous video, which I will put somewhere, as a bullet somewhere, we have seen basically that if a particular function like this, like phi, is a function of a complex number, so a function of a single variable, and you put in there a complex variable z, then in that case we are going to get some conditions or some equations that are satisfied by the partial derivatives of the various functions here that we see u and v. Okay, so that's something we've seen, and these are called the Cauchy-Riemann criterion. Now, as it turns out, what we can show and try to show is that if these particular criteria are fulfilled, then the only conclusion we can draw is that, at least in the context, for example, of integration, that it must come from a function of a single variable that basically is integrable. Okay, so basically that's what we're going to see today. Right, so just to set the stage a little bit, so what we had seen and what we are interested in here is a map phi, and this map takes basically a point of R2 and then returns a complex number. And the way it works in general is that it's going to take a pair x, y of real numbers, and then it's going to return a complex number, which is a function of x and y here, plus I, and then a function of x and y there. Now, what we are going to be interested in here is going to be an integral of a path. So that's in the complex plane, and that's an integral of a path that is so-called d gamma here, that is surrounding and enclosing a domain that I call gamma. Okay. Now, the particular form that I'm going, or differential form that I'm going to integrate here, is basically the following one. That's omega, so I'm calling it simply omega. That's a traditional notation for a form. And this is going to be phi xy dz. So basically I'm just saying this is the product of some dz, which is the, complex element in the complex plane, so dz. And then times phi, and that's it. So I'm not basically kind of specifying anything. And upon doing the calculations with the algebra of complex number, especially that I squared is equal to -1, then you end up with this particular equation. And essentially what I'm going to do is denote this omega r for the real part of omega, and here omega I for the imaginary part of omega. Okay, so that's what we get. Now, what I'm interested in is basically the following. I want to evaluate what is the integral of omega over d gamma. Okay, and if I want to make things very clear, and for once here I want to, so I'm going actually to write a circle here in the notation to indicate that I'm looking at the integral of omega along this particular path here. And so it's a closed path. That's what basically I want to conclude or to look at. Okay. Now, what I'm going to do is use the fundamental theorem of exterior calculus when it comes to integration. So what that means is that provided these functions u and v are well defined, okay, they are well behaved, and the derivatives are also well behaved, then I can, so basically there is no singularity anywhere here, then I can write the following. I can write that this is equal to d omega gamma. Okay, so that's the theorem that we've looked already at, like in multiple occasions for multiple things, including general relativity. And so here we just want to apply it in the context of complex numbers. Now, one of the things we can see is that, of course, it can be split into the real and so it's going to be d omega r plus I d omega I over gamma. Okay, and so I'm going here to evaluate these integrals separately, and we're going to see what these things look like. So so for example, let's look at the integral of d omega. So in fact, maybe let's calculate d omega r first. So what we have is that we've got d omega r is equal to du wedge dx, and then minus dv wedge dy. Okay, and then the only thing I do is that I substitute du and dv with their differential, their total differentials, and so that's going to be du dx plus du dy okay, and that's wedge dx, and then here I'm going to get minus, so I've got dv dx plus dv dy, and that's wedge dy. Now, please remember, we are working in exterior calculus. Maybe I can put it here. So what that means is that we've got dx wedge dy is equal to minus dy wedge dx. And we also have dx wedge dx is equal to dy wedge dy is equal to 0. So if I apply this particular algebra here, I'm actually going to get the following thing. So I get basically I get d, let's get this straight, so yes, so we get minus du dy plus dv dx wedge, not wedge, sorry, and so that's going to be dx dy. Okay, so that's d omega r is equal to that. Okay, and then we can do the same for d omega I. And so d omega I is going to be, so I just need to start from there. So that's going to be dv wedge dx, and then plus du wedge dy. And so let's try to do that on one line. So dv dy, the only part, so the dx part is not going to matter. So I'm going to get, here simply directly dv dy wedge dx. Okay, and here I've got du dx, and then wedge dy, dx wedge dy. Okay, and so consequently what I get is the following. So I get that I put this dy dx is equal to minus dx dy, and so we are going to get du dx minus dv dy, and this is actually dx dy, and so that's basically what these two are. Okay, now as it turns out, sorry, I forgot the d here. As it turns out, the things that I'm going to frame, okay, so I'm going to frame here two equations. They are the basically the Cauchy-Riemann criteria. So if I actually look at that, okay, and then I equate that to 0, and I look at this, and I equate it to 0, then basically these are the Cauchy-Riemann. This is a Cauchy-Riemann criterion. Okay, but what is fascinating is that if what we have shown here is that if the Cauchy-Riemann criterion is satisfied, so this is 0 and this is 0, then we've got that that is 0 and that is 0. Okay, and so I can say here that I get that this is equal to 0, obviously only in the case of Cauchy-Riemann. Okay, so that's not true in all possible cases. And what is fascinating is that this is for any gamma. Okay, so that's for any domain gamma and corresponding border, let's say d gamma. The only possibility for the integral of a curve and essentially of a path that you can represent in terms of an equation in z in the complex plane, because this has to be the case. If you move in the plane xy, then you can represent that as a path that is followed by a complex number z. Then what that means is that the only possibility for that to be 0 for all possible paths is for is basically so only possible if omega is equal to f of z dz, and where the f here is a function that is differentiable of a single variable, and then that basically where you substitute z inside. Okay, that's the only possibility for this to be true. Okay, and this is really related to the equation equal to 0, because if you only have a function of a single variable which is differentiable and also kind of integrable, so it has an antiderivative, then from this it follows that you can write it as follows: d of f of z, and where basically f prime of z is simply going to be lowercase f of z. Okay, so that's basically only possible in that way. Okay, so here we've shown that if these conditions are actually satisfied, then essentially all possible integrals of a closed contour is going to be 0, which in the context of complex analysis leads automatically to the fact that there is a function f of z integrable and differentiable, such that you've got f of z dz is equal to the uppercase f of z. Okay, so otherwise what that means is that phi is equal to lowercase f of z. Okay, and so here we've shown the second kind of complementary part of this criteria. We had shown the first thing, which was that if phi is equal to some f, then they satisfy this equation. What we've shown here is that if actually the Cauchy-Riemann criteria are satisfied, then it's basically the only conclusion possible is that it corresponds to a form like this. Okay, so I hope you found this helpful. It does also reuse quite a bit of external calculus, and so I think it's always good that we revise a bit of this. And basically that's it. So if you've got any comments or questions, by all means, do let me know in the comment section. And otherwise, see you in the next video.